We have seen the Shannon Hartley theorem and seen what it says. Now we shall see the proof for Shannon Hartley theorem. Now it is not the exact proof of the Shannon Hartley theorem. The exact derivation for the capacity of the Gaussian channel is formidable. So what we do is that we take a M-array PCM system and find what would be the channel capacity of the Gaussian channel for an M-array PCM system. So now consider, for the purpose of transmission over the channel, the messages are represented in the form of fixed voltage levels. So we have seen a simple PCM system. In a simple PCM system, what we are doing is that we would be representing the messages as in two terms, that is 0 and 1. So there are only two options which we have. The messages can be represented in two levels, that's 0 or 1. But we have extended it into an M-array PCM system. So M-array PCM system would not be sending only zeros and ones, but it would be sending certain other voltage levels as well. So I may have, say, different voltage levels. So in between 0 and 5, I will have, say, 0, 1, 2, 3, 4, 5. So different voltage levels I can send. So here, when it was 0 and 1, maybe we had sent only two voltage levels, 0 and 5. But in an M-array PCM system, depending upon the value of M, if at all M is 3, or if M is 4, or if M is 5, we can have different levels which can be possible. That is called as an M-array PCM system. Now, the sources generate one message after another in a sequence, and the transmitted signal is a waveform. So in simple words, if at all we had, say, 1, 0, 1, 1, I would have a waveform which is like this, right? 1, 0, 1, 1. But if it is an M-array PCM system, if at all it tells me, say, 1, 2, 5, 1. So I will have 1 volt, 2 volts, 5 volts, and then again 1 volt. So somewhat like this signal I would get. So we shall see an example, we shall take a particular sequence. Now this is one of the example which we have taken in order to do this derivation. So this message is at a particular level. Then during the second time interval, another level. During the third time interval, it takes another level. This level. Fourth time interval, it is taking some negative. Fifth, also some negative. This is the sixth, and so on and so forth. So this, whatever is shown here, it is a time interval t. So now what are these levels? You can see here there is no level at 0, but above 0 here there is a level which is lambda sigma by 2, and here below it there is a level minus lambda sigma by 2. So what is the separation between any two levels? Separation between any two levels is lambda sigma. So the next level above it would be nothing but, if at all I have lambda sigma by 2 plus lambda sigma, the next level here will be 3 times lambda sigma by 2. Negative level will be 3 times lambda sigma by 2, that is minus. Similarly here the next level will be 5 lambda sigma by 2, and here it will be minus 5 lambda sigma by 2. So these are the different levels which we will be getting here in this particular situation. So this is the sequence of messages represented by the waveforms S of t, and which assumes that different voltage levels correspond to different messages. So now the received signal is accompanied by noise, and this noise will be affecting the signal. So the root mean square value of this is sigma. Now I have not told you, I have taken these levels as lambda sigma by 2, 3 lambda sigma by 2, minus 3 lambda sigma by 2, etc. But I didn't tell you what is lambda and what is sigma. So assuming that there are even number of levels, the levels are located like this, plus minus lambda sigma by 2, etc. And if at all I had to take odd number of levels, then it would be one level would be 0 in the center and others would be lambda sigma, 2is lambda sigma, 3is lambda sigma, etc. So this lambda sigma by 2 extra is come because we are considering even number of levels. So there is no 0 is not considered as a level, so it is even number of levels. So the levels would be like 0.5, 1.5, 2.5, 3.5 like that. Otherwise it would be 1, 2, 3, 4 etc. But when you consider 1, 2, 3, 4, supposing you want from 5 to minus 5, how many levels will have? 5, 4, 3, 2, 1, 0, minus 1 up till minus 5. So it will be 11 levels. 11 meaning odd number of levels. But supposing if at all you start from 4.5, 3.5, 2.5, 1.5, 0.5 and minus 0.5, such a way that there will be how many levels? There will be positive levels 5, negative levels 5, there will be 10 levels. So it is even number of levels will be there. So most of the times for m possible messages there are m levels. Okay, so m messages are there. Depending upon m is even or odd, I can select the different levels. So assume that the messages are equally likely, and if at all the messages are equally likely, then the levels are also going to be equally likely. Now the received signal will be accompanied by noise, that I have told you, and the root mean square of this noise is sigma. So along with this signal there will be some noise also which will be present here. And what will be this sigma? Sigma is the RMS value of this noise. Now the levels are separated by an interval lambda sigma, where lambda is taken large such that it allows the recognition of individual levels with an acceptable probability of error. Now what does this mean? Now I have just drawn these different levels. Say there are, this is one level, this is another level, this is another level. There are just 3 levels, 1, 2, 3. I'll just show you 3 levels. Now sigma is nothing but the noise which will be here. Okay. Now this noise will be like this. Now what should be separation between these levels? Separation between these levels should be lambda sigma. Now what is this lambda? Lambda should be such a way that this sigma is, supposing it is lambda is very less, then what will happen is that the separation between these two levels will be very low. So the levels will come close to one another. So when the levels come close to one another, whatever noise is there here and whatever noise is there here, what will happen is that it will cross this division point. See, there will be some division between these two levels. So this noise can go above that threshold, that is here. Okay? And this noise can come below this threshold, so that it is difficult for us to recognize whether this is level number 3 or level number 2. So lambda should be selected such a way that there is sufficient separation between these two levels, and the separation between the two levels depends upon the noise value also. So if at all you know that this is large, that is, if at all your lambda value is more, then if your sigma is, your standard deviation is there, quite a lot of standard deviation is there, then the separation between them should be more. Okay, so I need to select lambda such a way that there is sufficient separation between the two levels or more than that. Okay, between all the levels. Now after having seen all these assumptions, now we have to find the channel capacity. So first thing is we find the average signal power. So we need to find the average signal power, and it is indicated by S. Now what is this? When you take average, it will be the sum of powers due to individual messages, and because it is average, we need to divide it by the total number of messages. Now what would this be? I can write as S would be equal to all the different levels which we had seen previously. We have to take them into consideration, all the levels, and we had what were the levels, and we have to take the power. So lambda sigma by 2 the whole square would give the power. I'm not considering the resistances. Then the level on the negative was minus lambda sigma by 2 the whole square, plus the next level on the positive side was 3 lambda sigma by 2 the whole square, plus minus 3 lambda sigma by 2 the whole square. Now how many such levels will be there? If at all there are m levels, and we are having, say, how many? If at all we have m different levels, and 4 are there on the positive side and 4 are there on the negative side, assuming that we will want even number of levels. So how many levels? The last level will be, supposing if at all we have 8 levels, m is equal to 8. Okay, so 4 levels will be there on the positive side, 4 levels will be there on the negative side. So this one would be lambda sigma by 2 minus 3 lambda sigma by 2 minus 5 lambda sigma by 2, and last is minus 7 lambda sigma by 2. So what is minus 7 lambda? Similarly here it will be 7 lambda sigma by 2. So if m is equal to 8, the last level is how much? 7, that is m minus 1. So like this I can go on and write m minus 1 lambda sigma by 2 the whole square plus minus m minus 1 lambda sigma by 2 the whole square. So this is what we get, and divided by m. So now we can simplify this, and since all of these are, this and this is same because it is squared, this and this is same, so I can write it at 2 times that. So S would be 2 by m, and inside the bracket I write lambda sigma square plus 3 lambda sigma square plus and last would be m minus 1 lambda sigma the whole by 2 the whole square. So I get this. Now from every term I can take lambda sigma common, okay, and I can take rather lambda I can take lambda sigma upon 2 the whole square, and inside there would be 1 square plus 3 square plus last would be m minus 1 square. So now what is this? This is sum of odd number squares, sum of odd squares I can say, from 1 to m minus 1, and this is nothing but equal to m into m square minus 1 by 6. Okay, this is the sum of squares of odd terms. So I can replace this last thing, signal S would be m and m will get m and m from the numerator denominator will get cancelled, and 6 and 2 and 2 will get cancelled, 1 6, so it will become 12. So this is the value of S that we now rearranging the equation number 2, what we have got here, I can take m on the other side, and I would be getting 12s. So 12s upon lambda sigma whole square would be equal to m square minus 1. So what I would get m is equal to 1 plus 12 raised to half. Now what is sigma square? Sigma square is nothing but the noise variance, right? So it is nothing but noise power. So I can write this m is equal to 1 plus 12 upon lambda square s by n, and this is whole raised to half. Now this is the number of levels. Fine. So now going further, we can say that okay, this equation I would just write it as equation number 3. Now since each message is equally likely, the average information, or that is the entropy, is given by it. If at all you remember, of equally likely, it is log to the base 2 of m. So I can substitute this is say equation number 4. So I can substitute this m. So it is log to the base 2 1 plus 12 on lambda square s by n, and this raised to half, it is bits per message. Now we need to find the information rate, that is R. We need to find R, and in order to do this, what we need to do is that we need to estimate how many messages per unit time are carried by. So now we assume that the bandwidth of the signal is B, and also we assume that now this is your analog bandwidth, okay, analog signal rather. So the analog signal is sampled at Nyquist rate, and see, because finally we are transmitted digital signal, so the main signal, which is analog, is converted into digital by sampling it at the Nyquist rate. So what will be the sampling rate? The sampling rate Fs would be 2 times Fm. So Fm, that is the maximum frequency, is nothing but B here. So it would be Fs is equal to twice B samples per second. Now each sample here is rounded to the nearest level. Okay, it is not that, so we are doing quantization here. So the moment each level is rounded off to the nearest level, hence we have each sample which will represent one message, and therefore the same is the message rate as out. So the message rate, which is nothing but R, which is nothing but 1 upon T, is nothing but 2 times B bits per second. So now from this message rate we can find the information rate. What is the equation to get the information rate? R into capital H, where R is nothing but twice B. H we have got from equation number 4. What is H? Log to the base 2 1 plus 12s upon lambda square into n raised to half. This half I can take it out of the logarithmic sign, so it becomes 2 into 1 by 2 b log the base 2 1 plus 12s. So this and this would get cancelled. So finally I can write R S by N. Now, by taking necessary precautions to ensure that the channel is just able to allow transmission with acceptable probability of error, we can say that this is R is approximately equal to C. So we can write that we can write this equation for the channel capacity. Now what is the thing is that still we are not done. So we are going to select the value of this lambda such a way that this 12 upon lambda square is equal to 1. So we take let 12 upon lambda square be equal to 1 and lambda square be equal to 12 such that lambda will be equal to square root of 12, which is 3.46. So we select the value of lambda as 3.46. It should be sufficiently large, that is what we know. So we select the level in such a way that it is 3.46 so that this equation becomes like this. So this is a simplified equation for the channel capacity. Now this is bits per second. Now this is a very important equation which we have derived here, that is your Shannon Hartley's theorem. So it gives what would be the channel capacity of a Gaussian channel, or rather a channel in which there is Gaussian noise. So now after this we have to check what would be something like Shannon's limit, and we can also find there is Shannon's limit, and then there is something called as bandwidth and signal to noise ratio trade-off. So these are the things which are remaining in this particular part.